In order to determine the minimum compression in the spring having a stiffness of 15 kilonewton per meter so that the wedge will not move to the right if a load of 250 newtons is applied pushing it towards the right, whereas we are neglecting the weight of mass A and B, and the coefficient of static friction for all contacting surface is given as 0.35. Additionally, we are neglecting the friction at the rollers as well. Now, in order to determine that compression of the spring, first of all, let's go ahead and figure out the resistive frictional forces on the contact surface between the mass of object B and the wedge at A. To do that, let's develop our free body diagram first. Here I have a load of 250 Newton that is pushing the wedge towards the right. So that is the direction of the impending motion. Therefore, the resistive motion or the frictional force will be opposing that direction and it is pointing towards the left. Starting with the frictional force between body B and A is given as F1, whereas the normal is given as N1. Similarly, we will have a frictional force between the wedge and the surface that is inclined at an angle of 10 degrees. So the frictional force will be along the surface given as F2, and the normal force will be normal to the surface that is making an angle of 10 degree with respect to the vertical axis. Now, once we have developed our free body diagram, one key point to note here is since we are given in the problem that the wedge is on the verge of slipping, therefore we can apply our relationship between the frictional force and normal force, that is equals to frictional force is equals to the coefficient of static friction times the normal force. So both the frictional forces can be represented in terms of the normal force as 0.35 N1, whereas the frictional force at the base between the wedge and the ground is given as 0.35 N2. Now, once we have listed out all the internal forces and external forces, let's go ahead and apply our equilibrium condition next. Starting with summation of forces acting along the y-axis, that is vertical axis, equals to 0. In this case, we have a normal force of N1 going in the downward direction. That's why I have negative N1, whereas N2 is pointing upward, but it is making an angle of 10 degree with respect to the vertical y-axis. So to project it along the y-axis, we have utilized cos 10 function. Finally, I have the frictional force F2 that is making an angle of 10 degrees with the horizontal x-axis. So to project it along the y-axis, a sine function is being utilized, and since it will be pointing in the downward direction, I have the negative sign next to it. Simplifying, we can get the value of N1 in terms of normal force N2, that is coming as 0.9233 N2. Next, let's go ahead and apply our equilibrium equation along the x-axis equals to 0. In this case, I have an external load of 250 Newton that is pointing towards the right. That's why it is taken as positive, whereas the frictional force F1 is going towards the left and equals to 0.35 N1. Similarly, our frictional force F2 is also going towards the left, but it is at an angle of 10 degrees with respect to the horizontal x-axis. That's why we have to project it along the x direction utilizing the cos function. Finally, our normal force N2 is also projected along the x-axis by taking the sine function. Simplifying and plugging in the value of N1 from equation 1 into our summation of forces along the x direction equation and solving, we can calculate the value of N2. In this case, the value is coming as 250 divided by 0.8412, that is equals to 297.2 newtons. Now, once we have the value of normal force acting on the surface in between our wedge A and ground, we can go ahead and plug that value of N2 in equation 1 to solve for the normal force between the body B and A, that is coming as 274.4 newtons. Now, once we have this internal force, let's go ahead and figure out the compression in the spring. To do that, we have to draw the free body diagram of our mass B. Here, first of all, we have to draw the outline. Since I have a rectangular shape, let's give it a rectangular shape outline. Next, we have our spring that is connected on the upward end of the object B. So there will be the force in the spring given as F is equals to Kx, where K is the stiffness of the spring and X represents the compression. Next, since we have this object B in contact with our wedge A, there will be the frictional force and the normal force involved. Now, in order to identify the direction of the frictional force and the normal, it will be always opposite to the direction on the wedge. So if you look at the free body diagram of the wedge, the frictional force is going towards the left, whereas on our body B, it is going towards the right. Similarly, the normal force is pointing downward on the wedge, whereas on object B is going in the upward direction. Finally, since the frictional force of the roller is neglected, we will only have the normal force, and here we have represented the normal force as the resultant NR. Once we have developed our free body diagram, let's go ahead and write our equilibrium equation. Since we are looking for the compression in the spring, the x value, so we can go ahead and write summation of forces acting along the y-axis equals to 0. In this case, I have a normal force of 274.4 newtons going in the upward direction, whereas the spring force of 15 10 raised to power 3x going in the downward direction. Finally, simplifying and solving for the compression x, we are getting the value equals to 18.29 millimeters. This is the minimum compression in the spring so that the wedge will not move towards the right.